Just restart this, reset, start. Okay, is this clear? 6 questions, but is the last one? No, everything is clear. Okay. You're sort of breaking. You're taking this. You're taking these numbers, which have, you can imagine them as having about c log n digits, and you're viewing each block of about log n digits together as a character, as a digit, as one digit. Instead of like b bits, it's a digit. So for example, in this example, it turns out that I'm going to view it in octal, right? So if b is 3, I'm working in octal. Yes. If b is 4, I'm working in hex. Okay. And then if b is more than 4, I'm not sure how I would actually go about writing the things on the board. Now, so you can view these as n c-digit numbers in base b. We're talking about base 10, yes, yes. Yeah, so I'm not sure, that doesn't, yeah, okay, that doesn't work when I'm taking integer b to b, because 10 isn't an integer power of 2, but okay. So now I have these, I have these n numbers, each is a c-digit number in base b. Now I radix sort, okay? Now how long is this going to take? So how do you, let's consider radix sort instead of like just, you know, magic that somehow works. Let's think about, we view these numbers as a matrix, right? Which has n rows and c columns. And in each column of the matrix, it's got the digits in the, oh, I think I reused c in the lecture notes for 2 things. That's probably bad. But okay, in the ith row and the jth column, you have the jth digit of the ith number, right? Now what you're going to do is take each column and you want to radix sort the numbers. You're going to, working from right to left, you're going to take the columns and you're going to do counting sort on the column, right? And how long is that going to take? Well, what is the range of numbers in the column? It's between 0 and 2 to the b minus 1. And that b is ceiling log n, which is at most, which is less than log n plus 1. So you've got a range, the numbers in each column are in a range linear in n, right? So when you counting sort each column, and as you're counting sort, there's going to be an example. This is it's also, there's an example in the notes, the same example. But okay, so you're going to counting sort each column, right? So the column of digits, so the rightmost digits in the numbers, they're numbers. They're b-bit numbers, which means, and b is ceiling log n, which means they're in the range 0 to 2. So the numbers, well, the digits in each column are numbers in the range are, well, they're b-bit numbers. So they're in the range 0 to 2 to the b minus 1. And 2 to the b minus 1 is 2 to the ceiling log n. This is a log, yeah. Minus 1, which is less than 2 to the log n plus 1 minus 1. So this is this is equal to 2n minus 1. Okay? So it's from a range which is linear in n. Okay, each of the columns, the number in each column is linear in n, so you can counting sort it in linear time. Okay? Now, when you counting sort the numbers in the columns, you are people's asking about? Okay, so you can do counting sort on the columns, and when you sort the numbers, you're also moving the whole. You're not just moving the numbers around. You're not just moving the digits around. You're moving the whole numbers around, which are these rows in this matrix. Okay. So now I'm going to show you the fact that if you counting sort stably and you work from right to left, then you actually end up with the numbers sorted. How long does this take? Well, it takes you linear time on each column. How many columns are there? C. But C is a constant. So you sort in linear time. So now we have this theorem that if you have n numbers from a range which is polynomial in n, then you can sort them and they all fit in a constant number of machine words. Then they each fit in a constant number of machine words. Then you can sort them in linear time. Okay, so that actually comes up quite a lot. And so radix sort is magic, and it breaks lower bounds, but not really, because you have this assumption about the range. Okay, so let's just do an example, because I'm sure my explanations may be clearer in the lecture notes, except that I did write them at 2 in the morning, so maybe not. Let's just see if I can get away with leaving this on here so that you can check it while I'm going. Okay, so let's assume that we have these numbers x1 through x7, and these are binary numbers on 2, 4, 6. What, really? 2, 4, 6, 8. 8 digits? I thought these were on 7 digits. Okay. Anyway, it looks like they're on 8 digits. 2, 4, 6, 8, yeah, okay. Why did I choose a power of 2 as the number of? You don't have to, it works anyway. So it's on 8 digits, and now we have 7 numbers. And so let's take, so B equals ceiling log 7 equals 3. So we're going to break these into columns. 3, 3, 3, 3, 3. I didn't draw these very evenly. 3, 3. Okay, and then these 3. Oh yeah, okay, it does work out, because that's why I thought it was odd, because it's the power, it's 8, but it's not a multiple of 3. Okay, so like here, and here, and here, and here, and not like that, like this. Okay, so we're going to break them into, like viewing this as sort of a matrix, we break them into chunks of size 3, and then we write, so this is 4 and 1, it's 5, this is just a 1, this is a 2, so 2, 1, 5. So we write it in octal. Okay, so frequently people will write sometimes to indicate that this is a binary number and not just a decimal number with lots of ones and zeros in it, they will write 2. And then to show that this is not 215, this is an octal number, they will write parentheses around it with a subscript 8. Actually, I'm not sure people usually do that, but I have seen it done. Knuth does it, I think, in Art of Computer Programming. So now we have octal numbers with 3 octal digits. So everything, unfortunately, there's no 7. Okay, but everything is in the range 0 to 7. So 0 to at most 2 to n, I think. Right. So all of these digits are from a range which is linear in the number of numbers. Can you define stable? Stable means that if 2 numbers are equal in the input, then their order in the out. If 2 numbers are equal, if two elements of the input are equal, their order in the output is the same as their order in the input. Right? So when we had x4, x16, and x50 are all equal to 17, in the output we say x4, x16, x50. That's why, oh, I forgot to say how you do this. When you're going through the, maybe I forgot. When you're going through the array for counting sort, sorry, I'm a bit short on sleep. When you're going through the array and counting sort, you have to, before you report each linked list, you go to the end of the linked list and you report it backwards. And that way it's stable. Okay, so that's how you make counting sort stable. You can do other things. Okay, how do you get number 7? Is it log base 2 7? So B, 7 here is the number of numbers. Okay, it's the number of input elements, right? So there's, okay, yes. 3 is ceiling of log base n. B is log base, log n, ceiling of log n. Okay, so yes, it's because this way, remember, if we choose B like this, then 2 to, what are each of these numbers? Well, it's about 2 to the B, and 2 to the B, 2 to the log n is about n, and then you have the ceiling, so to make everything integer, so you end up with this 2, but it's still a linear range. How is it base 8? Because B is 3, so 2 to the 3, so a 3-bit binary number is between 0 and 7, which is a base 8 digit. Okay, good. Right. So what we do, and then we, to radix sort, so I'm just going to erase this. Now, the trick is you can do, there are most significant bit first radix sorts, but people actually, which I said in the notes, if you radix sort starting at the left, then if you get interrupted halfway through, then at least you've done something. I mean, the numbers which are much smaller than, if some number is much smaller than another number, then this number comes before. So it's sort of partly sorted. But people prefer, frequently for implementation purposes, they prefer working right to left, so least significant bit. Although in this case, we're not working bit by bit, we're working octal digit by octal digit. Oct, maybe? I don't know if an octal digit is called an oct, whatever. So what are we going to do? And the important thing is that we have to do, so we're going to counting sort each column, and we're going to do it stably. And the reason for that is if you do a least significant bit first radix sort and you do it stably, then you can forget about any column that you've already processed because it won't get messed up. Okay. Whereas if you work from left to right, then when you process some column, unless you do like partitioning in buckets and stuff like this, then you tend to mess up what you've already done. And if you work from right to left and you don't use stable sorting on the columns, then you mess up what you've already done. But let's just see that this works when we do it stably. So here we're going to get 1, 1, 0, it's first, and then, okay, well, here we have a 0, so we write down 1, 1, 0, it's smallest. Then we have a 1, so we write 3, 5, 1. Then this 2, we have two 2s, but it's important that we're going to write this one first. It comes first in the input, so it's going to come first in the output. So it's going to be 0, 6, 2, and then 1, 1, 2. If this doesn't work, I'm going to be really unhappy. And then we have no 3s. We have 1, 4, 1, 6, 4, and then we have two 5s. And so again, because it's stable, it has to be 2, 1, 5, followed by 2, 4, 5. Okay. So this is stably sorted on the last column. Now, I'm just going to check that this is recording again. Okay, I'm a bit paranoid about that. What happened here? I took the rightmost column, the least significant column, and I did counting sort on it in linear time, in O of n time. And I rearranged the numbers in the order of their least significant digit, and I did it stably. So this 2 comes before, this 0, 6, 2 comes before 1, 1, 2, so this 2 comes before this 2. This 5, oh, unfortunately we don't have any cases where this could be like 2, 4, 5, and we switch it. Okay, that's kind of annoying. But it's just something a problem that would get solved anyway, but you're not going to see it get solved. But okay, so now we took the last column, the least significant column, we radix sorted on that. Now we're going to take the second column and we're going to radix sort on that. So there's no zeros, there are 3 1s, and we're going to stably sort, so it's going to be 1, 1, 0, 1, 1, 2, and then 2, 1, 5. And then we have no 2s, no 3s, 1, 4, which is 2, 4, 5. And then 1, 5, so 3, 5, 1. And then 2 6s, and we do it stably, so it's 0, 6, 2, and then 1, 6, 4. Now the important thing is here, if we didn't do it stably, we could accidentally swap this order, which would mess up the relation that depends on this one. So these are tied on 1, 1, 0, 1 and 1, and 1 and 1. But because we've already sorted here, if these are equal, then the tie is broken on these two. Okay? And then we just do the right column, the left column, the leftmost column, the first column, and we're going to stably sort. So there's 1, 0, so it's 0, 6, 2, and there are 3 1s, and we do it in stable order. So it's 1, 1, 0, 1, 1, 2, 1, 6, 4, and then 2, 1, 5, 2, 4, 5. And then there's a 3, 5, 1, and yay, we have actually sorted the things. Okay, how long did that take? Well, it took about 3 rounds of a linear process and 3 is the size of the numbers, which I didn't map to 0, but okay, it's sort of the number of it's the size of the numbers divided by the number of bits in the numbers divided by log n. And so we said the numbers are bounded by a polynomial, so this is going to be like C. So header for each grouping. I'm not sure what you mean. So in this case, C is going to be, we've got 3 columns, 3 is a constant. So 3 is this C, and it's basically log base n of the size of the range. Okay, let's see what the header means. Okay, like a title, how sorted. Okay, so this one is just these numbers written in octal. This is this, but sorted on the least significant digit. And then this, so it goes from here to here, sorted on the least significant digit stably. Here to here, sorted on the second least significant digit stably. And then here to here, sorted on the most significant digit stably. And why is it 3n? The time is 3n. Yes, so we have 3 columns, and each, well, we have 3 sets. We break each number into 3 sort of blocks of B bits. Each bit, each block is a digit between 0 and n. Okay. Yes, okay. It's in the lecture notes and tutorials and office hours. Right now, we have to get going because we have to get through comparison-based sorting. So that was radix sorting. I just wanted to see you. I just wanted you to see, sort of as a reminder for later when I go through. And you think, but wait, I've heard that radix sort can do that. Radix sort and counting sort work by looking sort of inside the number, right? We're breaking the numbers up into bits. We're looking at the bits. Whereas comparison-based sorts don't, right? You don't get to look inside the number. With counting sort, we're doing direct addresses, and we're actually sort of looking at the numbers as pointers, as indices into an array. And comparison-based, in the comparison model, you're not allowed to do that. The comparison model, all you're allowed to do is take 2 numbers and say, is this one bigger than this one? Or bigger, or equal, less, whatever. So, for the rest of the lecture, we're going to be in the comparison-based model. Okay, we get rid of all of these. I'm pretty sure on the syllabus there's a link to Antti Laaksonen's competitive programming book. And I'm pretty sure he's going to do radix sort in that. It's also radix sort is in the introduction to algorithms, and it's all over the web. Okay, so now let's talk about comparison-based sorting. Comparison-based sorting, like you get to choose these 2 numbers and then just compare them. Now, usually this is weaker than, as long as the numbers fit in a constant number of machine words in the RAM model, you can do a comparison in constant time. So the comparison model is sort of weaker. We can do less in the comparison model, assuming that everything fits in a constant number of machine words. So that means that if we can prove an upper bound in the comparison model, it also holds in the word RAM model. If you can prove a lower bound in the word RAM model, it sort of also holds in the comparison model, except some people let you do other computations that don't involve comparisons for free. So you have to be a little bit careful how you interpret things. But let's talk about various sorting algorithms. I'm just going to check what I have these notes. Am I saying everything? Yeah, I got through this long example. So first, okay. So theorem, we can sort if everything's from a polynomial range, we can sort in linear time.